So thank you everyone for being back here after the lunch break. So yeah, it's really nice to be home again. Like eat some familiar food, have my favorite Fritz rhubarb schorle again. I'm not getting paid for saying this. I just like it. So what will we discuss today? Today we will discuss about like some things that were happening in and around the areas of tensor decompositions. In particular, I want to talk about like joint work, two different projects that I had one with Alex Casarotti, and the main focus on this talk is on a recent paper with Ben Lovitz on the algorithmic aspects of like certain tensor decomposition models. And we will see how we can like relate certain algorithmic aspects with geometric aspects. We will study a bit of an ominous object, which is called the contraction variety of a tensor, which is a variety that we can naturally associate with a tensor, and which in some cases helps us to compute tensor decompositions. So, what is an additive X-rank decomposition? We know what tensor decompositions are. We have seen them a few times. And additive X-rank decompositions are a slight bit more general. You start with basically any subvariety X of a space V. And X can basically be anything, except that if you take X maybe as a linear space, then I will judge you. But in principle, you are allowed to consider all kinds of varieties. And then we look at this problem to write a tensor as a sum of R elements of X. So we have a variety and we look at sums of elements of X. So clearly this lives in the span of X, yeah? Usually we assume that the span of X is the whole of V, so that we can represent everything in V as eventually as a sum of like elements of X. But we are looking at representations where like is fixed, where we're trying to really write it as a sum of not too many elements from X. So the minimum, if we have a decomposition where the R is minimal, then it is called an X-rank decomposition or an additive rank decomposition with respect to X. So, and there's like a lot of problems into this category that we already know very well. Who knows what matrix rank is? Of course, everyone here, right? Tensor rank, we also discussed this, is like you write a tensor as a sum of product tensors. And there's like tensor rank, there's metric tensor rank, there's all kinds of different things that you can do. And depending on which setup you have for matrices, the space V is just a space of all matrices, and the X, the variety, are the rank 1 matrices. Similarly for tensors, the V is like Cn tensor Cn times n times n, and the variety X are the rank 1 tensors. But there's also a few more exotic examples. For instance, if we have a skew-symmetric, I'm writing this as lambda 3 of C to the n. These are basically the tensors, the n by n by n tensors, which are skew-symmetric, which means like whenever you flip two indices, you get like a -1 of the entry. And such tensors, you can write them as anti-symmetrizations as a sum of anti-symmetrizations of rank 1 tensors. That is logical, right? Because like every tensor has a tensor rank decomposition. So you can anti-symmetrize it, and then you get like a decomposition where as like these wedge products. And what does this wedge mean? It basically means just we take the tensor symbol, this U tensor V, and then we anti-symmetrize it. And then of course for 3-1 we do it obviously, but then it's a sum over 6 different permutations. So this of course only makes sense for antisymmetric tensors, but it's like a natural thing to look at, that we don't look at what is the rank of a skew-symmetric tensor, but we look at how many wedges do we need to express it. And then we can of course also talk about symmetric tensors. The S3 of C to the n, this means an n by n by n tensor, which is symmetric. What notions of rank do we know for symmetric tensors? We actually know a lot, right? We can, for a symmetric tensor, we can look at the tensor rank, where we have like AI, tensor BI, tensor CI. This is the tensor rank. But we also can write it as like, maybe like as UI tensor D, and that is called the symmetric rank. And I don't know, are these the same or could these potentially be different? If I don't know, if you know something, then maybe you should put it on Archive or Vixra or whatever kind of publishing platform you prefer. This was like this was like a really famous conjecture. It's called Coman's conjecture, whether the RSIM and the R10s are the same, right? Let's not get too deep. Yes, but we don't know. So in order to avoid the controversy here a little bit, we can also look at the third thing that we can do with a symmetric tensor. We can look at the Chow rank. What is the Chow rank? We take a tensor decomposition here, like this, for a symmetric tensor. And then if we have for a symmetric tensor decomposition, then of course, we also can symmetrize this thing, right? We can take the S3 and then we basically take the AI1. Okay, maybe I should write this as AI1, AI2, AI3. And then if I have a tensor rank decomposition for a symmetric tensor, I can certainly symmetrize it. That is like AI sigma 1, tensor AI sigma 2, tensor AI sigma 3. And then I should normalize by 3 factorial. All right. And now for Chow rank, what we do is basically we declare this thing to be rank 1. So we don't really care about, we're not saying anything about the tensor rank or the symmetric tensor rank. We have a symmetric tensor and we are trying to write it as a sum of like as little as possible symmetrizations of rank 1 tensors. All right. That is also one possible thing that we could look at. So this slide is basically telling you about symmetric tensor rank. Everyone knows this very well. We have here a tensor has like symmetric tensor rank at most R, if it can be written as a sum of like AI tensor 3, which is like AI tensor AI tensor AI. And for symmetric rank, there's like a correspondence between symmetric tensors and polynomials, homogeneous polynomials. And if we use this correspondence, then what this equivalently means is that we have here a cubic form, and we want to write it as a sum of cubes of linear forms. And this is basically just by taking this tensor T, and for each argument, we plug in a vector of variables x1 to xn. So far, so good, I hope. Yeah? Okay, then why should we care about additive X rank? I defined a bit of a strange notion for you. That sounds like some very abstract nonsense maybe, and now I should give you a justification what kind of interesting things you can do if you study things that go beyond like the classical tensor rank and symmetric tensor rank. So, and there's actually a lot of stuff. For instance, in algebraic statistics, there are like Gaussian mixtures, and if you want to basically estimate the parameters of a Gaussian mixture model from its moments, from samples, from data that somebody gives you, then you actually have to frequently solve like some really weird problems where you're trying to, for instance, if you get like some samples that allow you to compute the degree 5 moments of a Gaussian mixture model, then actually you get polynomial, a cubic form, which has this a decomposition like this. It's like a form of like some Li tensor to the 5 plus 10 times Qi Li to the 3. Like you get like some strange weird monstrum here that looks a bit messy. But you have like some, well, the polynomials that have this form, you can pack them into a variety X, and then it's an X rank problem. So basically, X rank problems are the kind of problems where you try to write a tensor or a polynomial as a sum of weird things. There are also a few less weird examples, like for instance, in quantum information, if you have like a bosonic quantum system, you don't necessarily have to understand what it is. Basically, think of a system that's based on light, like a photonic system where you throw light at some stuff and then you observe what happens. Then basically, entanglement of these bosonic particles, that is modeled by symmetric tensor rank. But then if you have there are other particles, for instance, like electrons, or basically all particles that make of matter, they have a different symmetry. They are not bososymmetric, they are Fermi-symmetric, which basically means in tensor language that the tensor is antisymmetric. It lives in an alternating power. And for them, like a pure product state, an unentangled state is actually a wedge product. So that's why like looking at sums of wedge products makes sense, for instance, from a quantum perspective. It makes sense from all kinds of other perspectives. For instance, like what we saw today in the morning, Mateusz was talking to us about the Lagrangian Grassmannian. You could take the Lagrangian Grassmannian, which is like some alternating tensors and some elements up of this variety and ask, what is the rank with respect to the Lagrangian Grassmannian? That would be an X-rank problem. Other problems, like in circuit complexity, there are lots. Circuit complexity is basically how can we express a computed polynomial with the least possible amount of arithmetic operations. And there's like all kinds of like rank problems associated with it where you look at non-standard ranks. For instance, like power ring circuits where you take a form, Qi, which is not necessarily a linear form, and then you raise it to a power. Or the aforementioned Chow rank is actually really important in circuit complexity. And I drew a small cactus here for people who are interested in generalized additive decompositions. Maybe somebody mentioned it, and they also fall into this framework of X-rank decompositions. So there's a lot of interesting problems here around in the area that have all of the different applications. And yeah, and this is some argument why we should maybe care about X-rank decompositions in a more general framework.
How you count same size, but maybe X has more weight. You don't measure them.
Yeah, that depends. You can possibly do that, but I don't do it here. Yeah? Also because in all the examples that I will have in this talk, the X will be an irreducible variety, and then I think it's yeah. Yes, for the generalized additive decompositions, exactly. You don't have you have a reducible variety, and then these things become important to count. Which, yeah. Then it's actually a different thing whether you're trying to minimize the R or you try to minimize some weighted R. But that's a detail, yeah. But very good.
Join or display.
So, yeah, but as we're already seeing from the ongoing discussions, there's a lot of problems here, and I hope many here in the audience will like the problems that we're looking at. So, what should be the first two questions that you ask if somebody gives you a variety X? So, what would Mateusz answer to this question? Dimension and degree. I like to think about three different questions. So dimension and degree, of course, but if you look at this from this perspective of additive X rank, then the first question that I would ask is, what is the generic X rank? Yeah, what is the generic X rank, which means? That's fair. And the second question is the degree question. When is our additive rank decompositions unique? If you want. So the generic rank question, the A question, basically asks if somebody gives you a general tensor, yeah, then how many elements from X do you need to represent it? Okay? If you can choose freely from X, how many do you need to represent it? You could also ask, like, for not generic ones, but for additive rank decompositions, that's only ever a difference by at most a factor of 2, because every non-generic tensor is a difference of 2 generic ones. Okay? So this question about the generic rank is like one of the fundamental questions about X rank that you should ask. And then you can ask a second question. If your rank is sufficiently low, this means basically this system that you express your tensor as a sum of R elements from X is overdetermined, then you can ask if you have a unique solution. You can ask if you have a unique minimum rank decomposition, up to, of course, like permuting the summands. Okay?
But here you speak about
yeah, so the thing is, all X-rank decompositions, I like to study them over the complex numbers. I put the real numbers here because for the Gaussian mixtures, for the application, it only makes sense to look at real ones. But you can still study them over the complex numbers. Nobody forbids you to do so. And if you show identifiability over the complex numbers, then you also have identifiability over the reals. Yeah. Yeah, but good question, yeah. So when are additive rank positions unique? That's an important question. Non-defectivity basically means that the minimum rank decomposition, there are only finitely many minimum rank decompositions. And identifiability means that there's only one minimum rank decomposition. And then the third question is, when can we solve additive rank problems? When can we actually compute them? This is much harder. And you need to, on a case-by-case basis, usually invest a significant amount of effort to compute additive rank decompositions. Yeah, and we also will discuss this a little bit. So, what do we know for symmetric tensors? Basically, we have reasonable answers for all 3 questions. Yeah?
I had non-defectivity inside of the application. You say this is somehow
Yeah. So, okay, this is more for the experts, but if you have like this decomposition problem, you have your tensor, you write it as x1 plus and so on plus xr, then this lives in the art secant variety of your x, and then basically what you want to know if this has to see if this has finitely many decompositions, you basically look at the map from all the parameters, which is basically the x to the r, which goes to the secant variety x. Yeah, this is the map which basically parameterizes everything. And then if you want to know if this is finite to 1, then you look at the differential. And where does the differential go from? It basically goes from the direct sum of the tangent spaces to x to the sum of the tangent spaces to x. And then basically this is now non-defectivity in the sense of a map, right? You basically take the tangent spaces at general points and look if they form a direct sum. This is the question of non-defectivity. Yeah? All right. So for symmetric tensors, we know a lot of stuff. We basically have an almost complete answer to question A and B, in the sense that the generic symmetric rank is basically always like we take the V where our symmetric tensors live in, which is basically the V is just or the d-symmetric power of our C to the n. Yeah? And the X is the Dietz-Veronese embedding of C to the n, which is basically all product rank 1 tensors which are symmetric. And then we basically know we take dimension of V over dimension of X, and then we seal it, and this is our generic rank, which some exceptions where we have like ±1 or so. But in principle, we know this. And if our rank stays below this generic rank, then we are actually identifiable, then we have a unique decomposition. So this is the best we can hope for, basically. And on the side of algorithms, we also know a funny thing. We know that if we have a symmetric tensor, which is concise and of rank at most n. Now that's an actual restriction, because what is the generic rank for three tensors, for symmetric three tensors? Well, if you take the formula here, this is like n plus 2, choose 3 over n, right? And then seal. And this is O of n squared, right? And here we want it to be like very low rank. If we say it's almost only rank n, then the system is not only overdetermined enough that we have a unique decomposition, it's actually so overdetermined that we can use like some simple tools to compute the decomposition. And this is a very well-known theorem, but I don't really know who to attribute this to. There's like Prony and Sylvester, they solved it basically for the case where n is equal to 2. And Prony's result is very old, from 1795 or so. So Prony is basically, he's on the Eiffel Tower, like one of the mathematicians and engineers who have like their name on the Eiffel Tower. So you can imagine that this was like a very long time ago. And yeah. And somehow, especially in the computer science community, people also like to call this Jenrich's algorithm, after Robert Jenrich, who never wrote a paper on this, from what I know. But it's like a really funny story. He basically gave the idea of like a uniqueness theorem to another researcher called Harshman, and then he published some results on this. So it's, yeah, the origin story of this theorem is a little bit messy, but it is a very well-known result, and we know what to do for this case. And the nice thing is works via simultaneous matrix diagonalization. And yesterday, Pascal Coirin gave to us a lecture where he explained how to do this, how to employ this algorithm. And yeah, that's very good, because this means I don't have to explain everything. All right. Let's try to give a first answer to the questions A and B. If you want to say something in general for all kinds of varieties X in all kinds of spaces V, that's a bit difficult, but at least you can try to give an approximate answer. And what we did in like what I did like in a project with Alex Casarotti was like to look at varieties which are basically, they have like as a regularization for this theorem, you have like the variety X is G invariant with respect to some group, and it also lives in irreducible G module. So be careful, the irreducible here and the irreducible there mean two different things. One is irreducible as a variety, and one is irreducible as a G module. Yeah, so irreducible as a variety means it cannot be covered by two proper subvarieties. And irreducible as a G module means it doesn't contain a proper G submodule. So, and basically, this first condition that V is an irreducible G module, there you want G to be big. Then this is easier to achieve. And for the second condition, you want the G to be small, so that it's easier to achieve that X is G invariant. So this balances this out a bit. And if you have like basically a reasonable variety in a tensor space, like something that's somehow canonical, then often it will satisfy this. Like symmetric rank, tensor rank, there you all find like suitable groups also for rank and for Chow rank and all of these. You find suitable groups, which usually is just a variant of like GLN or GLN times GLN or so. And there you can basically show an approximate Alexander Hershowitz theorem, which says, yeah, we have like this parameter counting bout, dimension of X, dimension of V over dimension of X, but then we have this annoying extra term. But if the dimension of X is not so big, then maybe this annoying, if like this X is like a very small dimension, low dimensional variety in a big space, then maybe this extra term dimension of x does not bother so much. And also, if you stay away from this dimension of x over dimension of v over dimension of x, then you actually get finitely many minimum rank decompositions. And sometimes you can strengthen this to a unique minimum rank decomposition. That's like a really, really beautiful paper by Maserenti and Mella, where they show that basically you can go from non-defectivity to identifiability under some conditions. So, and what we immediately get from this is that the generic Chow rank of a 3 tensor is actually also order of n squared. Yeah, because it's like dimension of v is the n to the 3, or the order of n to the 3, dimension of x is order of n. And similarly, if we stay below the order of n squared, then we have unique decompositions, unique minimum Chow rank decompositions, at least generically. Yeah. For the 3 tensors, basically, for all the examples that I had before for 3 tensors, if you look at them, you always have that the dimension of x is just linear in n, right? Just like n, maybe n minus 1 or n minus 2, and so on. And the dimensions of the tensor spaces, they are like here. For the 3 tensors, they are like n to the 3. For matrices, you don't get anything out of this theorem, because like n squared over n minus n is basically 0. But for 3 tensors or higher, when you have like a variety which has like n parameters, then you're fine. Well, I mean, the thing is, if you could prove that the generic rank is like very close to this dimension v over dimension of x, this is basically the best thing you could prove. Like, usually most reasonable varieties have the generic rank close to this value. And basically what I mean is that this bound here gets the strongest if the dimension of x is small in relation to the dimension of v. Does it make sense? Yeah, and of algorithms, there has also been like some interesting developments where we had like some problems that were where we didn't really have algorithms like a year ago, and now we have algorithms. Basically, there is a new algorithm for skew rank, and there's a new algorithm for Chow rank. And the new algorithm for skew rank that basically uses like some nice Lie theory, like you take basically the orbit action on a tensor and then you differentiate it, and then you look at the kernel of this orbit action and then you view it as a space of simultaneously diagonalizable matrices, and that basically gives you the decomposition. Really beautiful algorithm by Nick van Nieuwenhoven. And then what we did basically we took this Pony-Sylvester-Jenrich algorithm and we adapted it so that it can solve Chow rank problems. And this is what I mostly want to discuss today. So Nick's result is for order 3 tensors, and then basically he gets a worse rank bound if he goes to the higher order. And our result is the linear time claim is only for order 3 tensors, and then basically we get better rank bounds if we increase the degree. So you can, if you have an odd order tensor, you can actually actually I have it on the next slide. So if you have a tensor in S2d+1, then you can basically go up to rank roughly n to the d. And this is actually also completely analogous with the Jenrich algorithm for odd order tensors that also has a generalization to odd orders. So, and funny is that we also need a bound here, which is basically dimension of this space of D tensors over like some CD minus CD, and this is actually the exact same bound that is from this theorem here. That is like one of the ingredients for this algorithm. At least for the higher order case. For the lower order case, you don't need it. Okay. Questions so far? Yeah. Okay, so this is like really a talk which will have a lot of funny definitions, I'm trying to convince you that O(n to the 3) is linear time. You might have heard that the Deutsche Bahn always defines a train to be punctual if it is like at most 6 minutes delayed. And this is like what I'm doing here. I just get a convenient definition because my tensor has like size n cubed, and linear time means basically the size of the input, right? Or like linear in the size of the input. So n to the 3 is linear time today. So, yeah. Let's go back to Chow rank. Actually, I must apologize to you because I mispronounced Chow rank for the first half of this talk. And this is a bit of a funny story because I have a neighbor in Copenhagen. His name is Chow. And at some point we were talking, he was asking me what I'm doing, and I told him I'm working on Chow rank problems. And then he was like, oh, there's like a mathematician called Chow. Is he from Hong Kong? Why would he be from Hong Kong? Then I looked it up on Wikipedia. He was from Shanghai. Yeah, and then he told me, yeah, because like this Chow, this is like the Cantonese pronunciation of this name. And apparently, Chow was actually called Zhou. And we have been mispronouncing him all the time because apparently he went to the US before the Pinyin transliteration system was invented. That was like somewhere in the 1950s where it was invented, and back then people used like all kinds of like local transliteration systems, and in particular, this is like the Cantonese way of spelling the name Zhou. And if he were from like Guangdong or somewhere in southern China, then maybe it would make sense to call him Chow, but I didn't find any evidence that he shouldn't be called Zhou. So actually, for the rest of the talk, I will try to call this the Zhou rank, but please forgive me if I mess up because I'm so used to saying Chow rank by now. Yeah, so this is really the talk of things that are like a bit funny named. We have like Yenri's algorithm, we have the Zhou rank, and we will see what else is about to come. So what is the Zhou rank? We are trying to write a tensor as a sum of symmetrizations of like rank 1 tensors. And basically we have, I like to write this basically suggestively with a product to suggest that it's like a symmetrized tensor. We can exchange around this, or it's just basically because I'm lazy. And we have the same dual viewpoint that we can view every symmetric tensor as a polynomial. And what does it mean? We basically look at a tensor polynomial f, and we try to write it as a sum of products of linear forms. This is basically what the Zhou rank means. And why is this interesting? This is interesting, for instance, from the viewpoint of arithmetic circuits. So what is an arithmetic circuit? I actually don't know so well, but if you tilt your head a little bit, then it almost looks like a neural network. But it's not a neural network. It's basically a way to compute a polynomial with addition and multiplication gates. And this is called a sigma pi sigma circuit, where the sigma is a sum, the pi is a product, and the second sigma is again a sum. So basically, we have like, we're doing some, basically computing some linear forms, then we're taking the product of them, and then we're taking the sum of all the products of linear forms. So basically we have a product and then a sum. So it's like kind of like a sigma pi circuit. Where's the last sigma? The answer is it's actually in the linear form, right? Because the linear form is like a sum of the variables. Okay, so basically this is why this is called the sigma pi sigma circuit, and people in an arithmetic circuit complexity, they care about the top fan-in of the circuit, which is like how many edges do you have here to the second layer, which is exactly the Zhou rank. All right, let's do some practical examples. What is the Zhou rank of x1 cubed plus x2 cubed? In polynomial notation, in tensor notation, this would be e1 tensor 3 plus e2 tensor 3. It's at most 2. Someone has been answering very carefully. So who thinks it's 2? Who thinks it's 1? Who thinks it's 0? I'm glad that nobody rose their hand. So what is it? So certainly, this is like at most 2 because we wrote it as a sum of 2 products of linear forms, products of 3 linear forms. And then the question is, can this be like, I mean, we took like 2 different variables, right? There's no way that this could possibly have like some like strange way to write it as a product of other linear forms, except that every bivariate form factorizes as a product of linear forms, right? So we have here that this is actually, if we take the 3rd roots of unity, which are exactly the roots of this equation, if after we dehomogenize it, we get actually that this is a product of 3 linearly independent linear forms. So yeah, so the chow rank of this thing is 1, but the symmetric tensor rank is 2. All right, now let's prepare a bit for the algorithmic work. So this is like my favorite new variety. Well, what do we want to do? We have a tensor, and basically, I really like food, and that's why I like to imagine a tensor as a loaf of bread. So you can imagine that you have like a loaf of bread in front of you, and what do you want to do with a loaf of bread? You want to slice it. You want to cut it in slices, right? In fact, you don't actually have to imagine a loaf of bread, because I brought one. And I need a volunteer who cuts a few slices of this 3 tensor for the audience. Would you like to? All right, please. No, I don't think so. Well, I mean, every time you have a symmetric rank decomposition, you can it is also a chow rank decomposition in that sense. But it's like a bit, you know, the thing is like your measuring thing is basically a chow rank 1 term is like naturally more expressive than a symmetric tensor rank. So actually the answer to your question should be yes. Yeah, the chow rank is always smaller than the symmetric rank, because every symmetric rank decomposition is like yields you also a chow decomposition. Yeah, but usually it will probably be lower. Well, we don't know for concrete things. Yeah. Yeah. Yes, exactly. Okay, so we need to start cutting the bread, otherwise the thing doesn't the whole thing doesn't work. Can you do the cutting? Nobody will get murdered, okay? Just be careful with the knife. There, like, here's some things where just cut a few straight slices, like you see on the image, okay?
Okay, but general or
No. That's someone knows what's about to come. I did not pay this gentleman. So don't cut everything yet, because actually I need a bit of the bread left for the non-straight slices. Like, yes, first cut it like a reasonable person would cut their bread, okay? So how do we define the contraction variety of T? Well, we basically look at all the linear combinations of slices, and we take those linear combinations which are not full rank. That's actually a bit of a bad definition. For a tensor, what you actually should say is that the contraction variety contains those contractions F for which the rank of TF is lower than the rank of a generic contraction TF. And then it will be very similar to the variety of collineations or so that Mateusz knows very well. I think more or less there's probably some connection, but I didn't think long enough about it. So, and we are basically looking at the singular matrices in this span of matrices. Okay, and then let's start by my personal favorite way of like thinking about this algorithm, even though it maybe should not be called Jenry's algorithm. So if we have a concise symmetric tensor of symmetric rank n, that's like the assumption of Jenry's algorithm, then we can actually show that this contraction variety is a union of hyperplanes. And we will see that these hyperplanes, the irreducible components of the contraction variety, they exactly contain the information about our rank 1 decomposition. So why is that? So we have it that the tensor can be written as a sum of AI tensor 3 for some AI, because the rank is n. And we know by conciseness, if you don't know what conciseness means, basically just take it ad hoc here that it means that these AI have now to be linearly independent. And then when we look at contractions, how do they look like? They're basically inner product of AI with F, AI transposed. And the AIs are linearly independent. Now, when does such a matrix have full rank? Well, this will always have full rank if the AIFs are non-zero, right? Because we have a sum of n linearly independent rank 1 terms. So basically, this has full rank if and only if this is non-zero for all I. This means the contraction variety is basically the union of all the perp spaces of the AIs. Okay? So, good so far? And now based on this, we can basically geometrically think about Jenrich's algorithm. So I called it my favorite algorithm because I'm trying to avoid the name Jenrich's algorithm, but as you can see, I'm not very good at this yet. So we take a concise symmetric tensor of symmetric rank n, and then we output the unique minimum rank decomposition. This is basically the algorithm that Pascal Coiron showed us yesterday, so we can go over this a bit faster. But basically what we do is we have like this contraction variety, which is a union of hyperplanes. And if we have a union of hyperplanes, what does an algebraic geometer want to do? Do we want to intersect with a generic line, right? This is just, it screams to be done. So, because then we get like 1 point in each hyperplane. And we know already like the irreducible components, they determine our decomposition, right? Because they are the AIs essentially, or the perp spaces of the AIs. So what do? We intersect with a line. We compute the intersection points of the line with the contraction variety. And then basically on each of these intersection points hi, the thi will have a kernel. Otherwise it will be full rank. Okay? So basically we have these kernel elements. And now what do these kernel elements do? Actually, if you look back 1 page, these HIs are exactly, they are orthogonal to one of the AIs, right? So basically, we have like something like, is like, for instance, if our HI, our H1 is orthogonal to the first one, so we have like the sum of I equal 2 to n, AIF, AI transposed. Yeah, this is TH1, sorry, and this should be an H1, because the H1 is orthogonal to A1. It cannot be orthogonal to any other one. Why can it not be? Because the H1 would then lie in, for instance, A1 perp intersected A2 perp, and then this generic line would intersect a codimension 2 subspace, which it cannot do, right? So it can actually be orthogonal to precisely one of them if we intersect with a generic line. So now we have this equation TH1 x1, the corresponding kernel element that's like this thing. This is 0, and this basically, if you work it out, is I equal 2 to n AI H1 x x1 AI times AI, and the AIs are all linearly independent, so it follows that these things, they all have to be 0. So basically it follows that actually the x must be perpendicular to aj for each j which is not 1. So basically we have computed a vector which kills everything except for the a1. So we computed a dual basis of the AIs. And once we computed a dual basis of the AIs, we just have to apply TF to xi, and then we get a non-zero multiple of AI. And that's how we recover the decomposition. So this is, if you want, this is the geometric version of Jenrich's algorithm. Does this make sense? More or less? Or was it too fast? Good? Yeah? TF is now a symmetric tensor. This slide is still about symmetric rank. It was just recalling the definitions. And then the Zhou rank will come on the next, slide. Ah, okay. Yeah, fair, but I think this is coincidence. Yeah, maybe. I'm not sure if there's a connection there, but this is like, yeah. Okay. And now the nice thing is that was very surprising to us. By the way, you can distribute some of the slices among the audience if somebody's hungry. So, but the thing that is was super nice for us was basically that also for a concise symmetric tensor of Joe rank n, the YT, the contraction variety, is still a union of hyperplanes. This was like really nice. And how do you show that? Well, you take some decomposition, and basically what the assumptions mean is that the AIK in the decomposition, they have to form a linearly independent set. And then you basically write MI for each like of the Joe rank 1 terms. And then what the linearly independence means is basically that the image of TF is the direct sum of the images of the MIFs. Okay? And what does this direct sum condition mean? Well, when we have an F which makes the rank of TF drop, that's actually only possible if the rank of one of the MIFs drops. Okay, because of the direct sum condition. And that's a nice thing, because this means that basically the contraction variety only cares about what happens on the rank 1 components. So it's like certainly a union over I equal 1 to n of something that makes of the contraction varieties of like the MIFs. So we only are left to understand what the contraction varieties of the MIFs are. And that's basically how we get it now. Yeah. So after working out when MIF drops rank, we will see that this is actually exactly when the F is orthogonal to either of the AIKs. And why is that the case? Is this slide okay? Can I go to the next one? Yeah. So why is that the case? Well, we work it out quickly. If we have like a Chow rank 1 tensor, we can use the GL invariance. We can assume that AI1 is E1, AI2 is E2, AI3 is E3, standard basis vectors. And then we basically have a 3x3 matrix. And if we write alpha, beta, and gamma for the inner products of F with E1, E2, and E3, then this matrix, this Joe rank 1 matrix, in these coordinates looks exactly like this. This is a matrix here with like gamma, beta, and alpha. And the determinant of this is 2 alpha, beta, gamma. So somehow magically, the rank drops below 3. The determinant of this thing goes 0. And only if alpha 0 or beta is 0 or gamma is 0, which means exactly that F is orthogonal to A11, A12, or A13. Nice. So this is what we wanted. And there's a small difference. Basically, the kernel vector this time. Last time, the kernel vectors, they were dual basis elements. They won't be that anymore. This is like different for Joe rank. The dual basis elements, they will actually also be orthogonal to E1, just like the H1. Okay. But this still allows us to get everything. So I collected a few contraction varieties here in case you're interested in. For symmetric tensor rank, they look like this. For Joe rank, they look like this, union of hyperplanes. And for skew rank, they're a bit nasty. They're actually a union of codimension 3 hyperplanes, which makes sense because for skew rank, you can never distinguish between AI1, AI2, AI3, and any linear combination of them, any like linear transformation of them. Okay? And then there's also so-called W states that Matthias talked about. When you look at AI1 squared AI2, where this is like symmetric tensor product. And these are like some kind of like tangential decomposition to symmetric rank. There you have actually also a bit of a funny behavior. There you get only the AI1s matter for the Joe variety. Which means that actually if you solve that thing later, yeah, you have to watch out a little bit. So now let me try to briefly tell you how you solve these problems, like intersecting the Joe variety line. It's basically what you do is you solve this via a generalized eigenvalue problem. You take this Joe variety, you know that it's a union of hyperplanes, and now comes your time to shine. We basically take a generic TF and a generic TG. What this basically means is you take your loaf of bread and you cut it like a really stupid person would. exactly. So this might not be super practical, but the thing is, taking this TF and TG, this means that you define a line on this contraction variety. You define a line and you want to intersect it with the contraction variety. Basically, if you do one strange generic cut and another strange generic cut, then if you interpolate between these two, you will find in between n contractions for which the rank drops. And this is basically means here, you have like, in this visualization, you have like these blue lines. They are, these lines, they are basically the hyperplanes in your hyperplane arrangement, which is the contraction variety. And the red thing, this is not a hyperplane, this is a line. But it looks the same because I drew it in P2. And I drew it projectively, that's why it's on a sphere. It's just that, so that it's easier to draw. And what this means is basically we pick these two slicings and we then compute all of these intersection points. And that's how how do we do that? Basically, we search for determinant of TF minus lambda TG is equal to 0, which means exactly this can be reduced to an eigenvalue problem. And this is now exactly what we saw in Pascal Courant's talk. This is this TG to the minus 1 TF. So we solve a generalized eigenvalue problem and then we're good. And this is how we solve this thing in practice. All right. Now I'm going to briefly discuss to you how to apply this for Joe rank. We basically do the same thing as for symmetric tensors, except we need a few extra steps. Because if we go back, the problem is that the Joe variety, the contraction variety for the Joe rank is like a union of hyperplanes, but it doesn't tell you which hyperplanes belong together. So we need one step where we kind of group the eigenvalues and eigenvectors together, where we find out which ones belong to the same rank 1 term. And that's basically the main thing here. So we have like this contraction variety. We compute the generalized eigenvalues and eigenvectors. And then we have a test here, which basically returns 0 if and only if, returns something non-zero if and only if like the two eigenvectors, the two generalized eigenvectors belong to the same rank 1 term. And the test works like that. You take your tensor and the eigenvalues were calculated with respect to contractions TF and TG. And now you take another generic contraction TL. You have to take another one. And then you take this test xik transposed, sorry, times TL times xi prime k prime. All right. And then basically from there you can, if you're careful enough, then you can from there extract the decomposition. That's basically how it works. Once you have the grouping, you can basically compute the spaces of AI1, AI2, AI3, because this is just the TL applied to the generalized eigenvectors xi1, xi2, xi3. And then AI1 is the unique vector in UI, which is orthogonal to both hi1 and xi1. And it's a 3-dimensional space, so you have like two orthogonality relations, and then you can compute it from that. And then you need to correct missing scalars, but this is also possible. You have to be very careful to do all of this so that it actually runs in linear time. This is not so trivial, but you can do it. And then you have an algorithm for Joe rank. Nice. Okay. And maybe you want to also look at non-generic orbits, because right now we were looking at the setting where the AI1, AI2, AI3, they are all linearly independent. So, but there's also a few other orbits in the Joe rank. For instance, the Joe variety, actually it contains like E1 to the 3. It contains E1 to E1, E2, E3, the orbit of this one, where all are linearly independent. It contains the orbit of the W state, and it contains this other strange orbit. Okay? And what you can show when you're a little bit more careful, basically, you can show that basically a sum of W states you can also separate it. And then if you put a little bit more effort, then you are actually also allowed to basically mix different orbits together, because essentially a posteriori you can find out which eigenvalues belong to which orbits. You just have to be a little bit careful because over the complex numbers, the orbit of E1, E2, E1 plus E2, this orbit number 4, is actually E1 to the 3 plus E2 to the 3. So actually it's like the second secant of the 1-type orbit. And therefore the grouping in, if you want a minimal Joe rank decomposition in that case over the GLN E1 cube plus E2 cube, yeah, then you have to be a bit careful because it's like not unique up to, only unique up to grouping of like these symmetric rank 1 factors, pairs of symmetric rank 1 factors into pairs. Yes. All right. And maybe in the last 2 minutes, I will tell you how to generalize to odd order tensors. Basically, what can you do? You can take your tensor, you can contract it again. But if you have start with a symmetric tensor of order 2D plus 1, then you get a tensor of order 2D. This is not what you want. You want a matrix, right? But what can you do after contracting a tensor which has, after contracting the tensor, you can of course flatten it to a matrix. So you can flatten it to a matrix from SDC to the n to SDC to the n. And then this is actually now the TF. The TF is already the flattening. And then under some conditions, you can show that the contraction variety is still a union of hyperplanes and actually a union of all the hyperplanes that belong to the AIs that are relevant. This is a little bit more involved from the theoretical analysis because the direct sum condition is actually not so easy to verify by hand. And yeah, we needed to do some work there. For instance, if you just look at an order 5 tensor, then a generic TF, this will have actually rank 10 times RF. The R is not too big because, well, what happens if you have like one of these terms, if you have like one of these AI1 to AI 2D plus 1, you contract it, and then you try to flatten it to a matrix. Then the problem is that the image of this thing, this will actually contain all the possibilities to select D vectors out of these 2D plus 1. So this will be all like somehow all like square free monomials in degree D in those AIs. So this is written in the next slide. Basically, if you have a Joe rank 1 term, then basically the MAFs they will have rank 2D plus 1 generically, and then you can like for generic F, and then basically you can show that these are still in direct sum if you don't take the rank too large, and then in order to so basically this means that you can again understand the contraction variety by understanding the matrices corresponding to the rank 1 terms, to the Chow rank 1 terms, and then you need to understand actually when these slightly more complicated things drop rank, and therefore for that we use the eigenvalues of the Johnson graph. There's a bit of a combinatorial construction. Yeah, but that's basically it. So what did we do? What should you take home? Basically, what you should take home is that these additive X-rank decompositions, they are not as scary as they look like. If you have some kind of invariance, then they are often very well behaved. Especially Joe decompositions and skew decompositions, you can actually compute something. And also if you want to decompose a tensor into a sum of W's. And if you're interested about the algorithmic part, about the algorithms, then you can check out the paper with Ben Lovitz. And if you're interested about the more like additive X-rank decompositions, about non-defectivity and identifiability, then we have here a new project which basically generalizes the things that I showed you here to reducible varieties X. All right.
So a few quick questions.
Can you interpret the eigenvectors? So you mentioned the eigenvalues of your generalized.
In principle, for the Joe rank decomposition for the order 3, the generalized eigenvector is just another vector in this, which is orthogonal to AI1. So if you have like something like So if you have a decomposition here, AI1, AI2, AI3, then the HI1 will be orthogonal to AI1, okay? And the XI1 will be another linearly independent vector, which is also orthogonal to AI1. And now what happens when you take your tensor T and you hit it with the XI1, because the XI, this will actually be also orthogonal to all AJK, to all other parts. So if you contract it actually with the XI1, this will, first of all, this will kill all the terms which are not I. So this will actually be the contraction of AI1, AI2, AI3 with XI1. And then the XI1 kills AI1. So you have here actually, you should think of this as a tensor product where the AI1 can stand on the left side or in the middle or on the right side. And if it stands on the left side, it's going to get killed. So only the terms survive where the AI1 is on the right side or in the middle. So basically, if you contract twice, the AI1 will only survive if it's on the right side. So basically, this thing is a constant times AI1. So basically, these are some things that just help you to extract the AI1s. That's how I would interpret the eigenvectors.
That's a question.
I think Marcus had a question.
But I think it is a silly one. So I was just wondering where you need this X, whether G irreducibility would perhaps be enough.
In the initial theorem, like the... This one here? Yeah, because there is like some follow-up work also with Alex where we showed that you can still show something also when the X is not irreducible. But then you have to be a bit careful, like what is the dimension of X, right? You should maybe be careful because the secant variety will then be a union of joints, which all might have different dimensions. And then you actually should define non-defectivity and identifiability on a joint-by-joint basis rather than for the secant variety as a whole. So it becomes a bit more involved to state the theorem. And the proof is complicated.
Okay, so I think we thank Alexander again for a very nice and entertaining talk.